Hello everybody, welcome back. I am making an appendix to Lecture 2 to do two things. First is some corrections that were very helpfully noticed by two of you, and then add in the proof of the exponential law that I stated at the end of last lecture, but didn't prove. In general, please feel free to leave corrections for me. I tend to make a number of mistakes. I'm hoping to learn as much from this as you are. If you have corrections, please leave them in the comments. I'll be incredibly grateful. If there are enough corrections and enough extra material for me to make an appendix to the lecture, I will do so. If not, I will put corrections at the beginning of the next lecture, or whenever those corrections come up, I will make sure to address them. Okay, so let's start with the first correction. So the thing that I stated incorrectly was that a flag manifold is, as a set, is the set going up to Km of vector spaces V1 up through Vm where each Vi is a subspace of Rn with dimension equal to Ki. What I should have said is that the flag manifold f of n colon k1 up through km is the set of subspaces v1 through vm such that each vi is a subspace of Rn. Also, vi is a subspace of vi plus 1, and the dimension of vi is Ki. So, for example, a flag, so in f of 3, there is a flag and remember, f of 3 means complete flags, so where Ki is equal to I, and it goes all the way up to Kn minus 1. So in f of 3, there is a flag. Let me do a poor job of drawing 3 space. So for example, we could take the plane given by, so that's the plane given by x plus y, sorry, it's the plane given by x equals y, and z can be anything. There is a vector subspace of this plane. This plane also goes out that way, but the important thing is that it crosses the x-axis, the z-axis. That's the z-axis. It crosses the z-axis, and in fact contains the z-axis. This also contains, as a subspace, the line x equals y equals z. And then that contains the point x equals y equals z equals 0. So the flag is R3 contains the set of points x equals y, contains the set of points x equals y equals z. So that's a complete flag. Okay. Another correction. What I said is that omega of x is the topological space of maps from the circle into X. That's not true. This is a notational mistake. There is a thing that is maps from the circle into X. What I should have said is that omega of the pointed space x comma x0 is equal to the space of pointed maps from S1 pointed at, well, whatever, but there's 0, for instance, into x pointed at little x0. Of course, there is a thing called C S1 into x, and this can, I think there are different notations that you might come across. We could call this lambda of x, and this is called the free loop space. Okay, those are our corrections to the last lecture. Now let's give a proof of the exponential law. The proof that I'm gonna give is following Bredon's amazing topology book, which is called just Geometry and Topology. And it's Chapter 7. Oop, that was messy. Chapter 7, Section 2. And let's remember what the statement of this exponential law is. I'm going to phrase it slightly differently from how Bredon phrases it. So let's let x, y, and z be Hausdorff topological spaces. And assume that x and y are locally compact. Then there's a function from continuous maps from x cross y into z. First of all, this is just a function of sets from continuous maps from x cross y into z that takes a pair x comma y, takes a pair f to the function that takes little x to the function that takes little y to f of x comma y. There's a lot of parentheses. I'll state this in a clearer way in a second. And this lands in a priori just the set of functions as sets from x into the set of functions from y into z. The claim, there are two claims. The first claim is that actually this lands in the set of continuous functions from x into continuous functions from y into z. So this is a subset, and there's an inclusion here. So the first claim is that this diagram actually commutes. And the second claim is that this map is in fact a homeomorphism. The map here is frequently referred to as currying, or the Curry-Howard isomorphism, because this map makes sense when this left-hand side is replaced with arbitrary functions of sets. Okay, so that is our, for whatever reason my iPad has been freezing a lot lately. Oh, there it goes again. That is the statement of the exponential law that we will be proving. And we'll need a couple lemmas. The first lemma is going to help us prove, first of all, that we have this factorization. So we can take, if x is Hausdorff and locally compact, and y is just Hausdorff, then the evaluation map which takes a continuous function from x to y and a point in x, maps into y, this function is called ev, and what it does is it takes f comma little x and maps it to f of x. So this function is continuous. Let's give the proof. What color should I label proofs? I want to stay consistent for the rest of the lectures. If you couldn't tell, purple is my favorite color. Let's do red for proof. All right. So let's fix some f and x. And let O subset of y be an open neighborhood of f of x. So since f is continuous, there's an open subset of x, but because x is locally compact, we can even say a compact neighborhood K that contains little x such that f of k is contained in O. So by definition of the compact open topology, U of k comma O, which, if we remember, put a little thought bubble, is the set of continuous functions f mapping f of k, the subset of O. It's not always standard terminology. That's just the terminology that Fomenko and Fuchs use. So, by definition of the compact open topology, this is an open neighborhood of f. And so U k comma O cross k is an open neighborhood of the pair f comma little x. Okay, so that's the lemma. Let's give just a little bit of notation. This, I believe, is a little more standard. So, see, for fixed x, we write ev sub x. for the function that takes f to f of x. Secondly, if we're given a function from the product of x cross y to z, and say this is f, then we'll write f sub little x for the function that takes little y to f of x comma y. Okay, pretty straightforward. I just wanted to clean some things up. All right, let's state another lemma. Suppose that x, y, and z are Hausdorff, and x is locally compact. Then a function from x cross y to z, let's call this function f, is continuous let me move that down. By the way, I hope I'm using a narrower pen. I hope that's a little bit easier to read than my previous ones. I'll be working on making sure that my handwriting is perfectly legible the entire time. Okay, so this function f is continuous if and only if two things hold. First of all, for each little x in x, the function f sub little x is continuous and thereafter number two, the function from x to continuous functions into y cross z, sending little x to f sub x, that is continuous. All right. And just to clarify, the reason that this is an and thereafter is because this map actually lands in continuous functions from y to z because of the first claim. Okay, so 1 and 2 imply that f is continuous because we can write f factors as the function where we first go from x cross y then into C from y to z cross y, and this is via the map that takes x comma y to f sub x comma y, and then we take ev sub y into z. And both of these maps are clearly continuous. Ev sub y is continuous because of the lemma. Okay, so now let's go the other direction and show that these conditions are in fact necessary. So for the reverse direction, let's suppose that f is continuous. All right. So the first condition follows by factorizing f sub little x as the composite of y mapping via the constant map at little x. So this takes little y to little x comma little y. And if you really want to be super nitpicky about it, we can take y as a homeomorphism to the point cross y, and then this is the function point maps to little x, comma, the identity on y. Anyway, that may have been more confusing than helpful. So let me just clear that up. Okay, and then we factor that, followed by f. Right, so this ends up being f sub x. All right. So for the second condition, for condition 2, let's pick some little x in x, a compact K subset of y, and an open O, the subset of z, such that f is in U of k comma O. So continuity is something that can be checked on a sub-basis, and the UKO form a sub-basis of continuous functions from y to z. So all we need to do is we need to check that the preimage is open. So it suffices to show that there exists an open neighborhood containing x, open neighborhood W, nope, in goes the other way, an open neighborhood W, an open subset of x, such that for any any other x prime in W, we have that f of little x prime is in U k 0. All right. So since f is continuous, for every y in y, for every little y in y, there's an open neighborhood of little y again, I got the in sign backwards. Why do I keep doing that? There's an open neighborhood v sub y, of little y sitting open in big Y, and also an open neighborhood which you can call w sub y of x. That's a subset of big X. Such that f of w sub little y cross v sub little y is a subset of O. So by compactness, of y, did I assume that? Okay. I think I also need to assume that y is locally compact as well. So by compactness, we can write K as a subset of V sub y1 union so forth up to V sub yn for some finite n. Now if we set, let's define W to be W sub y1 intersect all of the other W sub yi up to W sub yn, we have that f of k cross W is a subset of f of v cross W, subset of O, whence the claim follows. All right, so that's that proof. And finally, we can get to the point where we can prove the lemma, the theorem of the exponential law. We can get the proof of the theorem. So by the previous lemma, we actually get the factorization through continuous functions from x into continuous functions from y to z. So it suffices. So we get this continuous function, and it is a bijection. Sorry, let me back up. We get a bijection just as a function of sets. So we need to show that this is continuous, and it will suffice to show that every subbasis element gets taken to a subbasis element and in fact and same with the inverse of that map. And when I say gets taken to, what I mean is that a subbasis element U ends up actually equaling its image. That U will. Okay. I'm saying this poorly. You will see what I mean once I start actually going through this proof. Okay, so pick some open in Z. And then K in X and K prime in Y compact. Then let's fix some notation. No, it's fine. Okay, then we have that F is in U sub U from K cross K prime into O, if and only if, well, first of all, if and only if for little y in K prime and little x in K, then F sub x of little y is in O, then that is true if and only if, okay, that's not actually a statement, so I should say for all. This is true if and only if for all x in little k, F sub x is in U of K prime, O, if and only if the whole function F sub blank is in U from K prime into from K into U from K prime into O. So because the K cross K prime give a subbasis for x cross y, then the U of K cross K prime into O give a subbasis of C from x cross y into Z. And similarly, the U k prime into O give a subbasis of continuous functions from y into z. And so the u from k into u k prime comma O give a subbasis for c from x into c, y into z. And clearly this is in correspondence with this under the bijection. So under the bijection, f maps to f sub blank u from k cross k prime into O ends up being taken to exactly u k prime into O. And that concludes the proof. I really don't like point set topology, but it's important to have that to have this exponential law. It's called the exponential law because sometimes people write c from x into y as y upper x. This is a category theorist kind of thing, and so what this ends up saying is that z upper x cross y is homeomorphic to z upper y quantity upper x. So it's similar to ordinary arithmetic, and yeah, okay, that's that lecture. Thank you for putting up with my mistakes and then my struggling attempt to get through point set topology. I hope to see you in the next one. Well, I won't see you and you won't see my face, but you know what I mean. Take care.